All right. So good morning, everyone, and thanks for coming. Can I record the meeting? Is everyone fine with it? Okay, perfect. So we have people on Zoom and in person, and today's agenda of the workshop is to get familiar with this programming language called Matlab. And the specific things that we'll cover in this workshop will be specific to what we need in this course, in this upcoming assignments. By the way, assignment 1 is going to be released today. So you will see that how the things that we are learning today will be helpful in solving your assignments. So MATLAB is not the compulsory language for this course, but it's a preferred language because it helps you to solve some of the signal processing techniques, and it has really great packages that can just do things out of the box. So you don't need to write as much code compared to like C or other languages. Python is a good option too, and you feel free to use any other language, but the primary support we'll provide will be for MATLAB. So there will be two things that we'll cover in the workshop. The first thing is getting familiar with how to code in MATLAB, which will be just some basics. And then we'll build a project which will plot the Fourier transform of our speech, of our audio data by recording it from a microphone and showing it as a visualization. So we'll do that project afterwards. So let's just begin straight away. I've already opened my MATLAB software, so feel free to, if you want to code side by side. As you can see, this GUI of MATLAB has a couple of windows. So on the left-hand side, you see the current folder or the project that we have opened. It has multiple folders in it that you can just browse. You can double click to open these files. And once you click them, it will open this script as a .m file in this window. On the right-hand side, you see that you have a workspace. This workspace basically shows what are the variables and the functions and all the data that you have on your current script or the current workspace that is running. And on the bottom, you see this command window. Now, this command window is basically just like a terminal, but it runs scripts or each particular line of code over here. So MATLAB is an interpreter language. So it runs a line by line, right? So you can just run anything on the command window, or you can bunch a couple of statements and put it as a script and run the script as a whole, just like Python, right? So to get started, let's look at some very basic syntax. So let's define a variable, let's say. So if we have a variable called a, we can just write a equals to 1, and that's it. We have a variable a equals. So if I run it over here, it creates a variable and prints out the current value. So if I have a equal to 5, it will say a equals to 5. Now in the script, there are two ways to write the statement. If you write a is equal to 1 with a semicolon, that means it will make the variable, but it will not print out this variable when you run the script. So let me run this script for you. And I have a button run. And it ran the test script, but it printed out nothing. But if I remove the semicolon and run it, it runs the script and also prints out the value. So this is a very good trick to debug your code while you're working. All right, so comment it for now. Now, to create a row matrix, a row vector, we can just simply use brackets and have numbers in it with comma separated values, and it will create a row vector, right? So we have a row vector here. But if you want a column vector, you can use semicolons in between these numbers, and that changes the dimension of the vector that you're creating. So if I run this line, now you see we have a column vector, right? So now let's say you have an unknown matrix. You also have a B, which is row vector, and A, which is a column vector. You can always look at the size of the matrix and see what are the dimensions of this. So it shows that size of A is 3 cross 1 and size of B is 1 cross 3. So this can come handy to know what is the current size of the matrices that you're using. Now, sum operators. Of course, there are basic operations like the sum is A plus B, where my A is 1, 2, and 3, and B is, let's say, 10, 11, and 12. Right? Now, if I do summation and run these three, we get the final sum. So this is the element-wise addition, right? And on the right-hand side, you see that as we are running these scripts, all of our variables are getting created in the workspace over here, right? So you can just go and look at their exact values, the dimensions, and every variable that you have on your current script. All right. And let's look at matrix multiplication. So if we create a matrix 5, 10, 15, and let's create a column vector so that we can multiply these two. So 1, 0, and 2. So we can create the product of this by simply doing A star B, right? But if you want element-wise multiplication, then you need to do A dot star B. Okay, so let's see what these two things do. So if this is another function that you can use to display any values, and this will just print it out, right? So now if I run the script, okay, I see. We run the script upon multiplying A cross B, we see that, oh wait, I should comment this out, otherwise it will print a lot of stuff. Okay, so display product of A and B. Okay, so it shows that product of A and B is 35. See, it's a single value because the dimensions of our matrix were 1 cross 3 into 3 cross 1. So the final answer is singular. Of course, if the dimensions are different, you will get the answer accordingly. And in element-wise multiplication, we see that we get, okay, so element-wise, we need to make sure that our matrices have the same dimension. So I'll just change them and run it again. And the final answer is 5, 0, 30. The second value is 0 because it multiplied 10 by 0. So we see that, yeah, it works fine. All right, I'll again comment these codes so that. Okay, so this is how you can handle matrices. Now, you might want to look at flipping a matrix. There's transpose, there's flipping left to right, up and down. So you can do all sorts of operations over here. So if you have A as a vector, you can have the flip of A by calling this function flip LR, right? It will just flip the vector from left to the right. And if you have a column vector, then you can call flip up and down. So flip UD, that should flip this upside down. So let's print both values. So if you see A and flip A, we'll print both. All right, so this is A and flip A. Clearly it's flipped, and similarly for B and flip B. Yeah, so these can be useful operations that you might want to use. Now comes complex numbers. I'm sure that professor has covered complex numbers and how important they are to represent signals. So we'll need to use a lot of them. And to create a complex number, the best way is to use this notation called J. So if you write 1 plus 2 J, or you can also write I. Matlab wants you to use J because it has better optimizations for it. It basically creates a complex number with the real part of 1 and the imaginary part of 2, right? So complex number has real parts and imaginary parts. It will just create that complex number. And if we print it out, it will show us that, yes, we have a value of 1. Also, let's just have another statement on the beginning of our script that simply clears our display every time we run the script. So it's have a less clutter on our screen. All right. So it creates A as 1 plus 2j. You can access the real part of A using real of A and imaginary part using imaginary of A. And so this basically creates real of A, imaginary of A. Similarly, you can also access the absolute value or the magnitude of this complex number, right? So if you do absolute of A, you get its magnitude or absolute value, complex number. And similarly, you can do angle. So angle gives you the argument or the angle this complex number makes with the x-axis, the real axis. So people can call it angle, you can call it argument, or you can call it phase. There are multiple notations for the same thing, but it basically gives you the angle this complex number is making. So if we do this, we see that it gives us the value in radians. So if we like have a familiar number, let's say 3 plus 4j, which we know is, sorry, let's take 4 plus 4j, so that we know it will make 45 degrees with the axis, and then let's see this number in degrees. So you have a function called radians to degrees, which simply converts this value in degrees and it will print it out. So if we do that, we see that it's 45 degrees. So that means 4 plus 4j, which is 4, 4 coordinate in the complex plane, does make 45 degrees. And let's say if we had 0 plus 4j, it should make 90 degrees because everything is in the imaginary plane, right? So yeah, I'll comment them out so that they don't display these values anymore. All right. Okay, so this was some very basic syntax. Now let's jump to some more interesting things of creating signals. So let's say you want to create a signal of your own. We just learned that we can create a signal using square brackets. Now, another cool trick, if you don't want to just keep writing numbers like this, you can also write the same thing like this using semicolons. So semicolon basically says that can you create a vector which starts from the value 1 and it goes to the value 4 at an increment of 1. So if I print these two things, we get the same answer, right? So 1, 2, 3, 4, a vector, we use a column to create a vector of which goes from 1 to 4 at increments of 1. But what if we want a different increment value and we want an increment of 2? So in that case, you can have the increment in the center of this syntax, and it will create a vector with increments of the same, right? So you can have any value here, and now you can easily create as long vectors as you want with whatever spacing we feel like. And the reason this is useful is that when we are creating a signal, we want to create a vector of time, right? A time which has like alternate values. So in that case, let's say our sampling frequency of the signal is 10 hertz. So we'll create a time vector which starts from, sorry, 1 second. Let's say we create a sampling rate of 10 hertz. So let's create a variable called 10, and using this, we'll create a time array which starts from 0, time 0. It forwards at a step which is higher than the sampling frequency. If you remember from the class, we studied Nyquist rate, which is, I don't know if Nirupam covered it. It did? Okay, perfect. So Nyquist rate basically says that any signal you have should be at least twice the sampling frequency of your signal. So if your signal is a 5 hertz signal, a sampling frequency should at least be 10 hertz. right? So here we are creating a signal. So let's create the signal which is smaller than your sampling frequency. So our sampling frequency is 10 hertz. So our Nyquist rate is 5 hertz, 10 divided by 2. So we can create any time array which follows this 5 hertz cap of sampling. So to be on a safer side, let's we take 0.5. Which 0.5 is the second, so it's half a second, basically 2 hertz, right? We can maximum we can go is 0.2, which is basically 5 hertz. For a sampling rate of 10, we use sampling rate of 5, which is 2. An easy way to do this is you can have a variable called period time, which is gonna be fs by 2. But it's gonna be inverse of this because the inverse of hertz is seconds. So this unit is hertz, and this unit is gonna be seconds, right? So our period time is the sampling rate of our signal. Perfect. And let's say it goes to 5 seconds, total duration of 5 seconds. So it's a time array from 0 to 5 seconds at interval of period time. Perfect. So now we can go ahead and create a sine wave. Sine wave is just a periodic wave that you can create using this function called 2 pi f. Sorry, sine. And sine simply takes these values of 2 pi f and time array. We haven't defined frequency of signal, so let's do that. Let's take a frequency of 1 hertz for now. Okay, but sine is a difficult array to just look at and see that what these values represent, right? So we can't figure out if it's actually a sine wave or something. We see some periodicity. Of course, these numbers are repeating, but we are not sure. So a good way to look at this is to visualize it, right? So we can create figures in Matlab just like Python. In Python, we have matplotlib. Similarly, here we have inbuilt functions to create plots. So if I plot the sine wave using the figure function, we created a figure and we simply plot the sine wave. So it should create a figure. I don't know, can people on Zoom see the figure that it created? If not, I'll just share it again. Okay. Oh, 1 sec. Can you see it now? Okay, perfect. So this figure, as you can see, it looks like sine wave. Of course, is discrete, so it's not as smooth. But the way to make it more smoother is you can either increase your sampling rate. So we can increase the sampling rate to 100, and our period time will change accordingly. Now, if we run it, see our sine wave is super smooth because it's sampling at 100 hertz. So we see the more smooth changes, right? So of course, the x-axis and the y-axis are not labeled. So we should do that. We should never leave our axis not labeled. So let's plot the time array along with the sine, so it knows what is in the x-axis. And then you can have x label to have time seconds, and y label to have your amplitude. Okay, now it looks good. It has time till 5 seconds. So now how can we create a 2D plot? So for that, let me create a matrix which is 2D. So this is a binary matrix with ones and zeros, and you can see that it's a 3x3 matrix with 3 rows and 3 columns. Now to visualize a 2D matrix, one thing that I like is the image SC function. Image SC basically plots an image, but an image is nothing but a matrix, right? So we can give it any matrix. So we'll give it A, and let's see what it plots. So here it picked yellow and blue as the color to represent ones and zeros. And if you see this, the middle row has all ones, all yellow colors. And then we have ones and zeros on the places where the blue is there, right? So this is how you can create 2D figures. Now, one advice I like to give you for assignment 1 is that you'll need to plot some 2D matrices. And when our 2D matrices are huge, we are trying to plot this huge matrix as an image on a tiny display. And what the display drivers of a laptop do is they try to compress it and show it in that area. So I would always advise you to increase it for full screen and see the proper information captured in this, because assignment 1 has very high frequency details in images. And often you see that if you change the size of the image will start to change. And that is not because the matrix is changing. It's just the display driver messing it up. And this thing is more common in the 13-inch laptop. So just an advice on how you should create figures on assignments. And that basically wraps up the basic thing. I'll also like to go through a quick demo of doing FFT, which is the fast Fourier transform on audio data in real time. So it's, I think it's a cool animation to see. I have the structure of the code here, which basically it says a bunch of stuff on how to get signal. It has a for loop, which goes to a variable called number of iterations, and then just ends. So this is how you can create functions. You have a function, the function name, the arguments that it might take, and you can run this entire function just by calling the script if the function name is same as the file. So if you see here the file name and same, so if I run this thing, it will automatically run the entire thing. Right now, of course, it's it says, okay, give me an error for number of iterations not defined. We'll just do that. But yeah, go ahead.
Before moving, can you show us the line that you included in the first file to clear the terminal, please?
Yeah, so it's, these are 3 different lines actually. The close all line closes all the figure windows that are opened, any kind of window that we have opened. Clear all clears your workspace. So it basically clears the RAM. So if you have very large data sets into your workspace, you can call clear that particular variable or clear all, and that will clear entire workspace. So it clears up your RAM.
Right.
And CLC is basically clearing your command window. So I can just call CLC and it clears the command window.
Thank you.
And
in this file, you utilize flip air.
Yeah.
And flip UD.
Yes.
So they have to be different if you are applying it to a column vector or
yeah, I mean, if you just have a row vector, then you basically the dimensions in the you just have one column vector. So flip up and down will just flip that one column vector onto itself, right?
Oh,
so it's, you can apply the operation, it will not give you an error, but logically it won't. You need more than one columns to apply flip UD. So that's why I take that example.
Good.
But you can apply any of these functions, and you can also apply flip LR on a single value. So it will still work, but it does not make much. Yeah.
In the, sorry, one more question about it. In the last line, you utilize image SC.
Yes. Image SC is used to visualize images. It's over here. Yes. I'll share all these codes, so you can refer them later in either the recording or the mat scripts also I'll share. Okay, so we are running a little short on time, so I'll quickly go through this FFT demo. So to start with, we have to first define the sample rate and duration, just like we did earlier. So I'll start with a sample rate of 8,000 Hertz. That's the typical sampling rate people use to capture audio data, the speech data, right? 8,000 is advised. You can also go higher depending on what we are using a laptop. So my laptop can go up to 96,000 Hertz, but we can keep it short right now. So this is a sample rate, and we'll have a frame duration, which is the total duration of each frame we'll take and apply F50 on this frame. Then let's see how many samples we have in this frame, which is nothing but our sampling rate multiplied by our frame duration, right? Come in this one. So if I run this, it should show the number of samples. Perfect. Okay, it shows that for a 0.1 second of frame duration, we'll have 800 samples, which makes sense for a sample rate of 8,000, right? Now let's create an audio recorder object. This is something that you might not need in your assignments. I'm just using it to capture real audio data from the microphone, but it's basically just an object that we used to capture audio data from any microphone. So if you have external mics, you can just call this and it will start recording data from it. So it's basically, it asks us to sample signal at FS sampling rate at a bit depth of 16 and just one channel of audio we need. So we should also define our total duration for which the script will run. So let's just call it for 60 seconds, which is 1 minute. Calculate the number of iterations that we should run the for loop. So we number of iterations, which will be our total duration divided by our frame duration. And then we can just start recording by calling the function record. Simple. So this thing is going to start recording as soon as we call it, right? So immediately after calling, we should start plotting what we are capturing. So first we'll create a figure and start a for loop. Right? Now, the way this record object works is that it will just start recording as soon as we call it, but our for loop is super fast. So we need to wait for some time to capture enough data, a frame duration worth of data, right? So there's a function called pause, which is literally just a delay that adds in this script line. So our pause should be equal to frame duration because that's how long our data is. And once we wait for that long, we can just receive the data from the recorder object. So there's a function called get audio data. Yeah, that's it. It takes your recorder object and it asks for the data type. In our case, it's double. Perfect. Now we have our audio data in this variable. This variable has multiple values in it. So let's take the index of the most recently acquired sample. So let's call it current sample. And now the way this audio data works, it's a continuously increasing vector, right? As we keep recording data, it gets populated in this vector and keeps appending the values as it captures the speech data. So the size of audio data is constantly increasing. But what we need to do is we'll have a sliding window, which takes a frame duration worth of data, plots it value on the figure, and then it slides it, plots the next one. So it appears as if it's a real-time thing. But in the back end, this particular audio data is a continuous increasing flow of data. And it will keep on going till our total duration. So till 60 seconds, we'll keep getting data in it, but we need some way to have our sliding window. So I'm creating this start sample, end sample indices to keep track of the window starts and end index, right? So it's basically gonna be our current sample minus number of samples, right? So this is our window length. And this is going to be your minimum of sample and the length of our audio data. Right, this makes sure that we always get the most recent frame from the data. And since audio data is a vector, we can just use these values to clip out values from this. So I think I skipped over this, but let's say you had a variable 1, 2, 3, 10, 12. One way to access a particular element is this, but another way you can access multiple elements is you can have 4 to 5. And now what this will do is it will slice the vector A from the index 4 to 5, right? So if I do this, it creates the values 4 to 5. And you can also do 1 to end, which is exactly same as just writing A, which gives you all the values, right? So we can, that's the same thing we are doing over here. To get the most recent frame, we are slicing audio data from the start sample to the end sample. Now, okay, now let's finally do FFT. So we can do FFT by calling this function. I think this is what is most useful for the assignment, that you'll often need to do Fourier transforms, and you should know how to correctly interpret the output of Fourier transform. So let's just call it signal for now. And the way FFT works is it gives you the Fourier transform, but it's not properly organized in the way it's so Fourier transforms goes from negative sampling rate to positive sampling rate. It's both negative frequencies and positive frequencies, but they are organized from negative to positive. It's not organized from 0 to positive and the way. So the way to do this is Matlab has this really good function called FFT shift. You should, anytime you don't know what a function does, just write that function and space help. Sorry, help space that function, and it'll print out the man page for this function. And you can always go and Google of what FFT shift does. So FFT shift man. So FFT shift, what it does, if you had a variable with vectors 1, 2, 3, 4, 5, 6, it flips them so that it gives the later half of the vector 4, 5, 6, and the first half of the variable, which is 1, 2, 3. This is just the way the output of the FFT is organized by default. It's a very language specific thing. Okay. So basically we'll take a FFT shift of signal and let's just overwrite this value. And before we do that, we also take the absolute, which is basically the magnitude of FFT. FFTs are always complex numbers, right? So to visualize it, we can't, instead of visualizing all complex numbers, we just visualize the magnitude of that particular complex number. So we take absolute, and then to get the single-sided spectrum, we take the FFT shift. Now it gives us the entire thing. And for the x-axis, we'll just define our frequency values, right? So frequency values corresponding to this. I'm sure Nirupam covered this in slides, so you have these formulas with you, but it goes from length of your frame, which is in our case recent frame, divided by 2, to our step size, which is fs divided by n. So in our case, it will be recent frame.
So in this code, we need the for loop to move the sliding window.
Yes, exactly. That's the coded part of for loop. So this thing goes from negative fs by 2, which is the length of our recent frame, at a step of till the value of our total fs by 2. So that's our sampling rate divided by the frame length. So this equation you can get in your slides. And finally, we should create a plot. This time we'll not call the figure because we have already initialized it. So in the for loop, we'll just update the figure continuously by calling the function plot. So we had our frequency values and the magnitude of signal. Did we define the magnitude? Oh yeah, it should call it. And just to make it look good, we can adjust some parameters of the plots like the line width and the colors, of course. And we have X label. Yes. Frequency in hertz. Right. And finally, it will only get updated if we call the function draw now. So this basically forces the figure to update with whatever the values are in the one. And that ends our for loop. Hopefully the logic is right. Let's see running it. But we also need to stop the recorder object, otherwise it will always keep on recording, which also can create errors if you try to create another recorder object because the microphone is already occupied, right? So we just make sure that we close it. And let's try to run this thing. Okay. Unrecognized function called audio recorder. Where is this? It should be called audio recorder. Device error. Okay, that's new. Is it because I'm sharing my screen or the mic is already occupied? Did someone write the code? Can you try running it if it's running, right?
Okay. Yeah.
It'll ask permissions for the microphone. I think I'm sharing my screen through HDMI and Zoom. It's giving me error.
I got the same error as you, but because of the audio recorded.
Okay, okay.
Oh yeah, microphone. So
Access
recorder is empty.
recorder is empty.
Yeah.
Oh, okay, okay. Let's see. Yeah, it's because of the Zoom issue. Let me just stop sharing the screen for a quick while and then try. Okay, and if I turn off this. Hmm. Let me just quickly connect my headphones and it has a microphone in it. All right, it's working. So the problem is that I'm trying to share my microphone between Zoom and HDMI and Matlab. So everyone is trying to access the microphone at the same time, which creates a conflict. And the way it worked is if I leave audio from Zoom and then run the script, it shows. So for now, I'll leave the audio on Zoom so people on Zoom will not able to hear me, but you will be able to see my screen and you can figure out what I'm speaking from that. All right, so I'll quickly, or maybe I can just try to change the microphone from Zoom. So microphone can take MacBook microphone. This thing can take, and MATLAB can take my headphones microphones. Hopefully that works. Let's see. Desktop. Let's just clear everything. Okay, yeah, this works. It's a bit laggy, but yeah, it's capturing my headphones micro. And if you see, the values are too large to be displayed. So let me call it. There's just one issue. This, which is that we need to shift magnitude of signal. Yeah. And we should also define our while limit values, which will be starting from 0. And let's say we go to 5. We'll change it if we think our visualization is not intuitive. Oh no, again this error. Did the microphone switch? Okay, let me just leave audio for a minute. Okay, if I join Zoom, okay, now it's still working. Perfect. So everyone has microphone access now. And the thing to notice here is that, first of all, this graph is symmetric about the y-axis. This is because it has both negative frequencies and positive frequencies. And this is because we are plotting real data, not complex data. So real data has both negative and positive frequencies. Another thing you see is that if I speak slowly, then the amplitudes are less. But if I speak loudly, then all these shows that all the frequencies have higher amplitudes. Sorry, go ahead.
Did you have to change something to make it more smooth into the code, or?
It depends on the frame duration. So I took a frame duration of 100 milliseconds. If you take it smaller, it will be more smooth because it will take smaller chunks. But it's a trade-off. If you take very small chunk of audio, the amount of frequencies that you're plotting will be less. So the frequency resolution and the time resolution has to trade off.
Great.
Okay, it stopped working. But okay, it stopped working because of the time offset, not because of microphone issues. That's good. Okay, I'm trying to play some specific frequencies using. I have an app called Function Generator, and this basically generates sine waves as audio signals. So I'll play this and hopefully get a peak in this visualization at that frequency. But will it run again? Okay, okay, still has microphone access. Let's create a, it might hurt ears a bit, so I'll start with lower volume. Okay, let's decrease the frequency actually, instead of. So I'm playing close to 370 Hertz. And if you see, we have this constant peak at this value. And if I decrease the volume, right? And let's change the frequency now. Okay, that's it for now. So yeah, it basically shows. Another thing you notice is it has some more peaks at multiples of that frequency, smaller peaks, so that are called harmonics. It's a cool concept, so you should read more about it. Yeah.
So just to summarize, you captured your audio, analog signal with your microphone, with your PC microphone. Then you try to convert that to digital with FFT, and you plotted the frequency.
Yeah, spot on. Just one minor thing is the analog to digital conversion is not what FFT does. FFT does time domain signal to frequency domain signal. But the analog to digital conversion happened in the hardware of the laptop. So we captured digital signal when we called audio recorder. And then that digital signal was time domain signal. By calling FFT, which is the fast Fourier transform, we took the Fourier transform of this digital time domain data, which converted to digital Fourier domain data, which is the frequency representation of the same time domain signal. So that's what FFT is doing. And the reason we did that is it becomes very intuitive to see frequencies as we were changing in this plot. Because time domain signal, if you look at it raw, you can just play around and instead of plotting FFT, try to plot the actual recent frame that we got, the variable. And you'll see that is just messed up waveforms coming in time, right? It's harder to interpret what this makes, but frequency opens up this new space to visualize and analyze these signals from, right? So that's what FFT is doing. And we keep on doing this in loop until the total duration empties and the loop cuts out.
Great. Thank you.
Yeah.
So with this, we can also create like a spectrogram.
Yeah, exactly. That's a spectrogram is basically doing Fourier domains in multiple time vectors and then making them in a 2D visualization where you show time and frequency as the same axis. And that's actually what assignment 1 is about. So you'll play with it.
Okay.
Yeah.
Okay.
Yeah. And do we have questions in the chat? I'll also stop recording and then you can just feel free to ask questions.